If you take a photograph of a car on a highway, you can see its exact position in that moment. But that single frozen image provides no information about where the car will be 10 minutes from now. Predicting a future destination, however, requires a tool that tracks the car's rate of motion in real time. This diagram shows two ways of looking at a car's progress. On the left, the odometer records the distance you've already traveled, a fixed measurement. On the right, the speedometer shows your current rate of motion. We face this same challenge when observing the natural world. Whether we are watching a falling object or a growing population, we can rarely see the final outcome immediately. We can only measure how fast things are changing right now. Scientists use a specific mathematical structure called a differential equation to bridge that gap. It is a formula built entirely out of these present-moment rates of change, used to calculate what the future will look like. We can see this math in action with a simple cup of coffee. When you set a boiling hot mug on a table, it begins to follow Newton's law of cooling. This chart tracks the coffee's temperature as it sits in a room. At the very beginning, when the coffee is much hotter than the air around it, the temperature drops rapidly. As the coffee loses heat, that cooling process becomes less intense. Because the coffee is closer to the temperature of the room, the rate of heat loss slows down. Eventually, the cooling process decelerates to a crawl. The temperature line flattens out as the coffee finally reaches the same temperature as the environment. The important thing to notice is the feedback loop. The rate at which the coffee cools depends entirely on how hot it is at that exact moment. This is the core concept of a differential equation. It is a way to describe a world where the speed of change is determined by the current state of things. When we translate that cooling feedback loop into a written formula, we have created a differential equation. In standard algebra, you solve for a single fixed number, but differential equations are used to find a continuous rule of behavior. The solution to a differential equation is a predictive curve that charts the future. Here, the formula expands into a continuous line graph, showing every state the object will pass through over time. This resulting curve allows us to pinpoint the state of an object at any specific minute. By following the line, we can see exactly how much the coffee will have cooled at any point on the timeline. Solving the equation essentially means using speedometer data to mathematically reconstruct the entire odometer journey. This method of tracking change is the key to unlocking almost every process in the universe. It is the same math that governs how radioactive elements decay, with the rate of disappearance tied to the amount of material left. It describes how electrical circuits build and store their charge over time. Engineers use these formulas to calculate the exact velocity a rocket needs to overcome a planet's gravity and reach open space. The same logic explains the structural curve of a hanging chain and the rhythmic, steady swing of a pendulum. You don't need to master the underlying calculus to appreciate the structural truth here. These equations are the point where pure mathematics meets the physical world. Mathematics is the language they use to listen to the rules of the present in order to understand the mysteries of the future. As Galileo observed, the great book of nature is written in the language of mathematics.